This lecture will cover the idea of estimating a population proportion using the techniques covered earlier on a point estimate and error estimate with a confidence interval. Previously, we've done this for population mean, mu, and our best guess for the population mean, mu, was our sample mean, x bar, and the confidence interval for that was our best guess for the population mean mu was the sample mean plus or minus some error calculation. When we're talking about a population proportion, what we're talking about is a percentage or fraction of the population that has a certain characteristic. So the classic example is opinion polls. If you want to know what percentage of Canadians support a particular political party, you would need to do a proportion estimate, this fraction estimate of the quantity of people that adhere to a particular political party. So an example would be if we're talking about political support estimates. You might have, let's say, P equals 0.32 or 32% support some political party A. Now you'll notice that this P notation is very similar to what we had already covered in the binomial distribution. And so we can actually talk about P as the population proportion that we're trying to estimate. In order to estimate this, we need some kind of sample estimate. And the symbol for the sample estimate is P with a little hat over top, this caret symbol. And this is the sample proportion. And the way that you calculate this is exactly the way that we did this with fundamental probability. It is the number of occurrences, or the number of people that adhere to the condition that you want, have the specific characteristic that you want, divided by the sample size. So that's the number of times that you find what you're looking for, that you find your success, divided by the sample size. So it is literally a measurement of experimental probability. It is the likelihood of finding what you're looking for in your sample. By definition then, Q hat is going to be the likelihood of finding a failure, or the likelihood you don't find somebody in the population having the characteristic you're looking for. And so it's just going to be the complement. It's going to be 1 minus P hat. And so this is going to be the number of failures, or the number of times you don't find what you're looking for out of the sample size. And so our best guess for the point estimate, the best guess for the population proportion, is the sample proportion. And our confidence interval is going to be that sample proportion plus or minus some error calculation. And when we do population proportions, there are no small samples. Every time we do this, the sample size has to be a minimum of a very large size. Otherwise, our error is going to be so large that it will just swamp our measurement. So we only use z-scores. There are no t-scores here. It'll always be the z-score for the confidence interval estimate, and we multiply it by the standard deviation over square root n. And when we're dealing with the binomial distribution, you may remember the standard deviation was related to the product of p and q. And if we divide that product by the square root of n, we get our error estimate for population proportion. And so remember, you can write that down in two ways. If you take the population proportion minus the error, that is going to be less than the sample proportion minus the error is less than the population proportion, which is less than the sample proportion plus the error. That would be the interval estimate. So you can write that in either of those two fashions. They are identical. So to do an example of this, let's say we wanted to estimate the percentage of Canadians that are over age 25. So estimate the percentage of Canadians that are over age 25. In order to do this, we have to take a sample of the population. And so if we take a sample of, let's say, 200 random Canadians, and we find that 146 are over age 25. Then our best point estimate, we have to know our confidence interval, so let's use a 95% confidence interval. Our best guess for that population proportion is our sample proportion. And so if we have 146 divided by 200, (146 divided by 200 gives us a percentage of 73%. If we need it, the sample non-proportion would therefore have to be 0.27, so that they both add up to 100% or 1. And so we need a 95% confidence interval. So here we have our sample proportion P. We're trying to estimate population proportion, or sample proportion P hat. We have to estimate population proportion P. And we're doing this with a confidence interval of plus or minus the error. If we have a 95% confidence interval, that means there is 5% total in the two tails, which means each tail contains 2.5%. So if we look up the area to the left of this z-score, it is 0.0250. And we can find the matching z-score on our table. So looking at the table of z-scores, we need to find an area of 0.025. And if you look at the areas, there's an area here, 0.025. That if we look at the intersection where the area 0.025 occurs on the table for z-scores, we find it is at minus 1.96. So that's for the area 0.0250. So the z-score for that value is plus or minus 1.96. The error in our estimate then, using proportions, is z alpha over 2 square root p hat q hat over n. It is going to be 1.96 square root of 0.73 times 0.27 all over 200 0.73 times 0.27 over 200 square root of that times 1.96 gives us an error of 0.0615. So, our conclusion, best guess for the population proportion is sample proportion plus or minus error is 0.73 plus or minus 0.06. Generally, the error is given to one significant digit. And so if you round this, you would have 0.73% plus or minus 6% would be the estimate of this proportion. Or if you wanted to do this with an interval estimate, then it would be anywhere from 67% up to 79% for the true population to lie. True population proportion to lie.